IRC 37 Flexible Pavement Design Part 1 Overview. Welcome to Civil Engineering Infrastructure. Today we are going to start the complete series of IRC 37 Flexible Pavement Design. This entire series is divided into a total of 40 parts. However, in this first part, we will cover the complete overview from slide 1 to slide 10. This means we'll cover the basics in part A. In the next parts, we'll cover advanced concepts in detail. So let's start the overview of part 1. Section 8. Part Introduction. Part Introduction is given first in the slide. This is part 8 of the IRC 37 Flexible Pavement Design series. And in this section we will understand the fundamental concepts of pavement design. That means only if your basics are strong, you will be able to understand the further design properly. An engineering note has also been given here that it is very important to have strong basics. Section 2. Content Structure. Now a table is given in the middle in which the complete structure from slide 1 to slide 10 is given. Now let us understand this one by one. Slide 8 we will understand Introduction to Flexible Pavement, i.e., its basic concept and definition. Components of flexible pavement in Slide 2. That is, what are the pavement layers? Load distribution mechanism in slide 3. That is, how the load is transferred between layers. Types of pavements in slide 4. That is, overview of flexible and rigid pavement. Flexible versus rigid pavement comparison in slide 5. Pavement layers overview in slide 6. That means complete layer structure. Subgrade and its importance in slide 7. That is, foundation behavior. Granular sub-base IEGSB layer in slide 8. Wet mix macadam IEWMN layer in slide 9. Bituminous layers IEBC and DBM in slide 10. That means in this part 1 we will understand the complete pavement structure step by step. Section 10. Learning Outcome. Now the learning outcome is given in the slide. What will you understand after this part 1? You'll understand pavement basics. You'll gain knowledge of all pavement layers. You'll gain a clear idea of load distribution. You'll understand the difference between flexible and rigid pavement. And the importance of foundation and material will become clear. Section 4. Flow Understanding. The flow diagram is given below. It tells us how to learn. First, we'll understand the basic concepts. Then we'll understand the layer system. Then we'll understand load distribution. Then we'll understand the materials. And finally, we'll be ready for the design stage. That means this entire learning process is structured step by step. Section 5. Pavement Layer Sketch. Now the pavement layer sketch is given on the right side. This shows the typical flexible pavement structure. The wheel load is shown at the top. And the layers are given below. Bituminous concrete IEBC. Dense bituminous macadam IEDBM. Wet mix macadam IEWMN. Granular sub-base IEGSB. And at the bottom compacted subgrade. This entire layered system transfers the load from top to bottom. Layer function explanation. Now the function of each layer is given below. The GSB layer provides support and drainage. The WMM layer distributes the load and provides stability. The BC and DBM layers provide a smooth surface and waterproofing. That means every layer has its own specific role. Layer Identification Summary. The layer identification summary is given below. GSB thickness is approximately 100 to 300 mm. WMM thickness is approximately 150 to 250 mm. DBM thickness is approximately 40 to 100 mm. BC thickness is approximately 25 to 50 mm. And the subgrade supports the entire pavement system. Practical Engineering Note. Now Practical Engineering Note is given on the left side. If the subgrade is weak, pavement failure will occur quickly. If the layer selection is proper, then the performance will improve. And load distribution is the key factor for pavement life. Bottom Summary. A quick summary is given at the bottom. In Part 1 we cover basics, layers, and load concept. And the most important line is, the foundation is strong, then the pavement will be strong. So friends, in this Part 1 we will build the entire foundation from slide 1 to slide 10. After this, in the next parts we will learn detailed design, CBR calculation, traffic analysis and pavement thickness design step by step. Stay connected with Civil Engineering Infrastructure. Thank you. SLID 1 IRC 37 Flexible Pavement Design. Hello friends. Welcome all of you to Civil Engineering Infrastructure channel. Today we are going to start a very important and practical topic. IRC 37 Flexible Pavement Design. Now if you are associated with highway engineering, road construction, pavement design or site execution, so this whole topic is going to be very important for you. Because the highway looks as simple from above, engineering is equally deep from within. And what is the most interesting thing? Road failure does not happen suddenly. Engineering reason hidden behind it. At some places the traffic calculation is wrong, at some places the CBR is weak, at some places the drainage is poor, and at some places the layer compaction is improper. Are going to understand this entire engineering philosophy in this series. So let's start with today's first slide. Introduction. Here is what is written first. IRC 37 is the guideline published by Indian Roads Congress for the design of flexible pavements. Now first of all understand here. IRC 37 is the official pavement design guideline of India, which is published by the Indian Roads Congress. And the major flexible pavements that are built in India, their design is mostly based on IRC 37 philosophy. Now look at the next point. It provides the procedure for pavement thickness design based on. And here are 4 things. This is the backbone of the entire pavement design. TRAFFIC loading. The first factor, traffic loading. Now imagine. A normal car is moving on the road, and on the other side there is an overloaded truck. From the outside, both vehicles may appear normal. But both do not cause equal pavement damage. Heavy axle load develops more stress inside the pavement. And if the design traffic is not calculated correctly, so after some time rutting, cracking, depression may start. This is why traffic analysis is so important in IRC 37. SUBGRADE strength. Now the second factor, subgrade strength. How strong is the soil below? And be honest, this is the actual hidden engineering. No matter how premium the road above looks, if there is a weak subgrade below, so the pavement will eventually show distress. Climatic condition. Now the third factor, climatic condition. Rainfall, temperature, moisture variation. All these directly affect pavement performance. Now imagine, if water infiltration starts in the pavement, so first of all the lower layers will be weak. And that's where pavement deterioration will start. Material properties. Now the fourth factor, material properties. If aggregate weak, bitumen poor quality or compaction improper, then the pavement will fail quickly. That means thickness alone is not sufficient. Material quality is equally important. Now look to the side. Widely used in national highways, state highways, expressways, HAM and EPC projects. That means IRC 37 is used in almost all major road projects in India. Now see main objective below. To provide safe, durable and economical pavement design. Now three things are very important here. Safe highway, durable pavement, economical design. That means the pavement should be such that it does not fail quickly, requires less maintenance, and does not increase unnecessary extra costs. Now let us look at the second topic of the slide. दो की definition. Here is the definition of flexible pavement. A pavement structure that transfers wheel load to subgrade through layered load distribution. Now this is the heart of the entire flexible pavement engineering. Wheel load does not go straight down. Rather it spreads layer by layer. And as it goes down, the stress decreases. Now look carefully at the right side diagram. Flexible pavement layered section. The wheel load is shown above. And what are the red arrows telling? The load is spreading while going down. Now let us understand layers. Bituminous layer. Bituminous layer at the top. This is the direct tire contact layer. It provides riding quality. Provides waterproofing. Receives traffic load. Granular base. Now below is granular base. It provides structural support and spreads the load. Granular sub-base. Now the GSB layer. It supports drainage and protects the lower layers. SUBGRADE. Natural soil at the bottom. Ultimately the entire load reaches this. And this is why weak subgrade can become a major cause of future failure. Now let us look at the third topic of the slide. 3 key components. Here are the main components. Bituminous layer. Granular base. Granular sub-base. Subgrade. Now in the coming slides, we will understand all these layers in detail. Now look at the formula box. Pavement thickness formula. T1D1 plus A2D2 plus A3D3. Here D bituminous layer thickness. D granular base thickness. D granular sub-base thickness. Now what is the actual engineering logic? Pavement performance doesn't depend solely on thickness. The quality and contribution of each layer is also important. Now look at the important point box. IRC 37 mainly focuses on fatigue cracking, routing failure, design life performance. And these are the actual highway failures that are most visible in the field. Now see the quick note below. Flexible pavement design depends mainly on traffic and CBR value. And be honest, these two things are the foundation of entire pavement engineering. Traffic and CBR. If this goes wrong, so the entire pavement design may become unsafe. And now in the next slides, we are going to understand traffic, MSA, CBR, subgrade and pavement layer behavior in a step-by-step practical way. SLID though. Scope and applicability of IRC 37. So friends, in the last slide we understood what is IRC 37 after all, and how the basic load transfer mechanism of flexible pavement works. Comes a very important question. Is IRC 37 applicable to every road? Is every pavement designed like this? And what is its actual scope? Understand this whole thing in a practical way. Ek scope of IRC 37. Here is what is written first. IRC 37 provides guidelines for. Now here it has been explained in which works IRC 37 is used. Flexible pavement design. First point, flexible pavement design. That is, what will be the thickness of the pavement, which layer will be how strong, how much bituminous layer should be given where. The design philosophy for all these things is provided by IRC 37. NEW pavement construction. Now the second point, new pavement construction. When a completely new highway is constructed. So traffic, CBR, climate, design life. Pavement structure is designed on the basis of all these parameters. STRENGTHENING and overlay design. Now the third point is very practical. Strengthening and overlay design. Now imagine. The old road developed cracks, the riding quality deteriorated, deflection increased. So the entire road is not removed. An overlay design is done on top of it. And IRC 37 also plays a very important role in deciding the overlay thickness. PAVEMENT performance evaluation. Now the fourth point, pavement performance evaluation. That is, how is the existing pavement performing? In that, how much is rutting, how much is cracking, how much is remaining life. The evaluation of all these things is also related to IRC philosophy. Now look to the side. Applicable for. Here's where IRC 37 is applicable. Highways, expressways, urban roads, industrial roads, toll roads. Understand an important practical thing here. Where repeated heavy traffic comes, their pavement design becomes even more critical. Specifically industrial corridors, mining roads, toll highways. Here the axle loading is very high. Now let us look at the second big topic of the slide. Though applicability. It is written here. Used for traffic ranging from low volume to heavily trafficked corridors. That means IRC 37 is not only for heavy highways. Can be used from low traffic roads to heavily trafficked highways. Now see suitable for below. Bituminous pavements. Multi-layer flexible pavements. Roads with granular and treated base. Notice one thing here. The entire focus is on flexible pavement system. Rigid pavement is not being covered here. Now design basis is given on its side. Design is based on cumulative traffic, subgrade CBR, climate, material strength. Now these four pillars govern the entire pavement design. Cumulative traffic. Only present traffic is not seen here. Future traffic growth is also considered. Because the road is not designed for today, it is designed for a service life of 15 to 20 years. SUBGRADECBR. Comes the same hidden hero again. CBR. If the subgrade is weak, then the pavement thickness will have to be increased. Climate. Drainage becomes more important in high rainfall areas. And bituminous layer behavior may be different in hot regions. Material strength. If the material quality is poor, then the theoretical design may fail in the practical field. Now let us look at the third topic of the slide. 10 important engineering note. It is written here. IRC 37 uses mechanistic empirical pavement design approach. Now this term is asked a lot in interviews. So understand it in a practical way. Mechanistic empirical approach. Mechanistic meaning. The load behave inside the pavement, how will the stress be distributed, where will the strain develop. This is scientific analysis. And empirical means field performance observations. That is theory plus field experience. And be honest, this is actual highway engineering. Now look at the right side diagram. Flexible pavement structure. Traffic loading is shown above. The layers below. Bituminous layer. Binder course. Granular base. Granular sub-base. Subgrade. Now here the wheel load is getting spread while going down. This is the layered load distribution mechanism. And this is the reason why the stress reduces as we reach the subgrade. Now let us look at the fourth topic of the slide. 4 key objectives. Here are the main objectives of IRC 37. Safe riding quality. Should be smooth and safe. Long pavement life. Road should not show distress quickly. Reduced maintenance cost. There is no need for frequent repairs. Better load distribution. Wheel load should be properly spread. Improved structural capacity. Pavement can carry heavy traffic safely. Now let us look at the fifth topic of the slide. Punch limitation box. Now this is a very important section. Because here it is said that IRC 37 is not directly applicable. Rigid pavements. Concrete pavement design. Airfield pavements. Now understand the practical thing here. Rigid pavement design is based on a different philosophy. Concrete slab behavior comes into it, the load transfer mechanism is different. Therefore, IRC 37 is mainly used for flexible pavement. Now see the quick revision note below. IRC 37 is mainly used for flexible pavement thickness design in Indian road projects. The main purpose of the entire guideline. Correct pavement thickness design. And now in the coming slides, we are going to understand traffic analysis. MSA calculation. Lane distribution. CBR and pavement layer composition with actual field logic. Because in highway engineering, decisions are not taken by looking at the surface. It is taken after looking at the structural quality inside. SLID theme. Flexible pavement components. So friends, till now we have understood. What is IRC 37? Where is it used? and what is its overall scope. But now comes the most important practical question. Flexible pavement made from inside. Which layer does what work? And how does the highway load reach the soil below? Understand this entire pavement structure practically layer by layer. What is flexible pavement? Here first of all the basic concept of flexible pavement is given. Now the slide says, flexible pavement is a layered pavement system that distributes wheel load gradually to the subgrade through different structural layers. Now what is the most important word here? Layered system. That means flexible pavement is not a single layer. It is a structural combination of multiple layers. Now look at the next point. Load transfer occurs from top layer to bottom layer in decreasing stress intensity. Now this is actual engineering science. Wheel load creates the most stress at the top. But as the load goes down, the stress decreases. And this is the reason why the subgrade does not receive the tire load directly. Now look at the third point. Pavement surface undergoes slight deflection under traffic loading. Understand a practical thing here. No pavement is completely rigid. When a heavy vehicle passes, so there is a slight deflection in the pavement. If the design is proper, then this deflection will remain within safe limits. But if the pavement is weak, so slowly rutting, cracking, settlement, start will happen. Now let us look at the second big topic of the slide. Though flexible pavement layer system. Now the layers of the entire pavement are given here. And be honest, this is the heart of the entire highway structure. Bituminous surface course. Top layer bituminous surface course. Now what is its function? Provides a smooth riding surface. Traffic wear and skid resisting. Protecting the lower layers from water infiltration. Now common layers are also given here. BC means bituminous concrete. DBM means dense bituminous macadam. Important point is written here. Highest quality material is used in the top layer. And that's absolutely right. Because this layer remains in direct contact with traffic. If quality is compromised here, so the overall pavement performance will deteriorate quickly. Base course. Now comes the base course. And this is a very critical structural layer. See its functions. Wheel load distribution. Providing structural strength. To reduce vertical compressive stress. Now look at the common materials. WMM. CTB. CTSB. Now the engineering note here is very important. Base layer carries major structural load. That means this layer controls a major part of the pavement strength. See sub-base course. Now comes the sub-base. Its function. Improve drainage. Stopping the pumping of fines. Providing a working platform during construction. Now here is the common material. GSB. The important point is written below. Proper drainage increases pavement life. Now be honest. Many times, the hidden reason for highway failure is drainage. Enters below. So CBR will decrease. Settlement will increase, and pavement distress will begin. The subgrade. Now at the bottom comes subgrade. That is natural soil foundation. Its functions. Supporting the entire pavement structure. Receiving the final load. Now here is the design parameter. CBR value. See the keynote below. Poor subgrade causes pavement failure. And this is the actual field truth. No matter how premium the pavement above is, if there is weak soil below, so the pavement will eventually fail. Now let us look at the third topic of the slide. Teen load transfer mechanism. Now the complete step-by-step load transfer is explained here. Step 1. Acts on the pavement surface. Step 2. Starts spreading from the bituminous layer. Step 3. The stress intensity decreases as we go down. Step 4. Large contact area reduces subgrade stress. Now this is the whole flexible pavement science. Now look at the big diagram on the side. Flexible pavement typical section. The tire load is visible above. The white arrows below telling stress distribution. The load is spreading while going down. And below it is written stress distribution decreases with depth. That is, the stress decreases as the depth increases. Now the functions of layers are given again on the side. A. Bituminous surface course. Function riding quality. B. Base course. Function structural strength. C. Sub-base course. Function drainage support. D. Subgrade. Function foundation soil. अब नीचे ड्रेनेज एक्शन डायग्राम देखिए. Is draining down. Now this proper drainage system increases the pavement life. Now let us look at the fourth topic of the slide. 4 important technical concept. It is written here. Thickness of pavement decreases stress reaching subgrade. Now what does this mean? The stronger and thicker the pavement, the less stress will go down to the soil. Now look at the formula box. Part engineering formula box. Text higher thickness, text lower subgrade stress. Now this is the entire structural design logic. Now let us look at the sixth topic of the slide. 6 keycap common pavement failures due to poor components. Here are the failures. Rutting, fatigue cracking, raveling, edge failure, settlement. Now in the next slides, we will understand all these failures with practical field examples. Now let us look at the seventh topic of the slide. 7 practical site observation. Now this section is very practical. Improper compaction of GSB causes settlement. If the GSB is not properly compacted, so voids remain below, and later settlement can begin. Low density in WMM causes rutting. If WMM density is not proper, so depression may develop in the wheel path. Weak subgrade increases pavement deformation. Weak soil always increases distress. Water stagnation damages pavement rapidly. Standing water is the biggest enemy of pavement. Now let us look at the 8th topic of the slide. Art interview question box. Q. Which layer mainly provides riding quality? Answer. Bituminous surface course. Q. Which layer mainly controls pavement strength? Answer. Base course. Now watch one short revision below. Surface layer, riding quality, base layer, structural strength, sub-base, drainage support, subgrade, foundation soil. And friends, this entire flexible pavement structure is the backbone of actual highway engineering. If layer composition is correct, compaction proper, drainage effective, and material quality is controlled, so the pavement can give safe performance for a long time. In the coming slides, we are going to understand the actual engineering of traffic loading and MSA calculation. From where the actual calculation of pavement thickness design starts. SLID chart. Traffic analysis in IRC 37. So friends, till now we have understood flexible pavement work, how is the load transferred, and what is the role of different layers. But now comes the biggest question. For how much traffic should the road be designed? How much load will it bring? How much will traffic increase in the future? And how many years will the pavement last? This is where it starts, traffic analysis. And be honest, if the traffic analysis goes wrong, so the entire pavement design may become unsafe. Ek introduction to traffic analysis. Now let us look at the first topic of the slide. It is written here. Traffic analysis is the process of evaluating traffic volume and axle loading for pavement design. Now here two words are most important. TRAFFIC volume. That is, how many vehicles are running on the road. AXLE loading. That is, how much actual load the vehicle is putting on the pavement. Now understand the practical thing. Pavement damage is not caused by vehicle count, but more by axle load. One overloaded truck can do more pavement damage than hundreds of cars. Now look at the next point. IRC 37 considers cumulative traffic loading during the design life of pavement. Now cumulative traffic is a very important term here. Because pavement is not designed only for today's traffic. Is designed for future traffic for the next 15 years. 20 years or more. Now the benefits are given below. Accurate traffic analysis ensures safe pavement performance, economical design, reduced maintenance, longer pavement life. Now imagine, if the actual traffic turns out to be high, and the design is done for low traffic. So quick rutting, fatigue cracking, settlement, start will happen. Now see the keynote below. Traffic loading is the most critical parameter in pavement design. And be honest, this line is the reality of entire pavement engineering. Now let us look at the second big topic of the slide. Two keycap types of traffic data required. Now here it is explained which traffic data is required for pavement design. A. Traffic volume. Now what is traffic volume? Vehicles passed in a specific time. Now what is it measured in? CVPD. AADT. CVPD. Commercial vehicles per day. That means how many commercial vehicles are running daily. AADT. Annual average daily traffic. The average daily traffic for the entire year. Now see the important points below. Commercial vehicles mainly affect pavement damage. And that's absolutely right. Pavement damage from cars is limited. But heavy trucks increase pavement distress rapidly. B. Axle load data. Now the second data, axle load data. The actual wheel load measurement is done here. Collected using weighbridge, axle load survey, WIM system. Now look at the engineering note. Heavier axle load causes exponentially higher pavement damage. Now this is a very important practical concept. If the axle load increases even slightly, so pavement damage can increase many times. This is the reason why overloaded trucks are considered the biggest enemies of highways. C. Traffic growth rate. Now the third parameter, traffic growth rate. Now future traffic increases every year. And IRC, 37 designs pavement considering the same future growth. Here are the typical ranges. 5% to 7.5%. Traffic will keep increasing every year. And if future growth is not considered, then the pavement will soon start showing distress. Now look at the right side typical highway traffic scene. Now here is the mixed traffic. Cars, bus, trucks, heavy commercial vehicles. And this is the actual Indian highway condition. Now look at the axle load illustration below. CAR 10 kN BUS 60 kN 2 axle truck 80 kN 3 axle truck 120 kN MULTI axle trailer 180 kN. Now understand the actual engineering here. The more axle load, the more pavement damage. See the wheel load distribution diagram below. The highest stress is above. And as we go down, the stress is decreasing. This is the load distribution mechanism of flexible pavement. Now look at the traffic growth concept graph. Traffic is gradually increasing. And this is why future traffic forecasting is critical in pavement design. Now let us look at the third topic of the slide. Teen design traffic concept. It is written here. Design traffic is calculated in terms of million standard axles (MSA). Now this is the most important term. MSA. Million standard axles. That is, how many standard axle repetitions will the pavement safely carry in its design life. In the next slides, we will understand MSA calculation step by step in detail. Now let us look at the fourth topic of the slide. 4 important formula box. The actual design traffic formula is given here. N 365 times A times frac 1 plus R N minus 1 R times F times D. Now here, N design traffic. A initial commercial vehicles per day. R annual growth rate. N design life. F vehicle damage factor. D lane distribution factor. Now this is the foundation of the entire pavement thickness calculation. Now let us look at the fifth topic of the slide. 5 traffic categories. Here are the traffic categories. Low traffic less than 10 MSA. Medium traffic 10 to 50 MSA. High traffic more than 50 ms. Now as MSA increases, pavement thickness will also increase. Now let's look at the sixth topic on the slide. 6 important engineering concepts. Commercial vehicles cause maximum pavement damage. Overloaded trucks reduce pavement life drastically. Traffic growth directly increases pavement thickness. Multi-axle vehicles distribute load more efficiently. Now this is the actual field logic. Now let us look at the seventh topic of the slide. 7 practical site observation. Incorrect traffic survey causes unsafe pavement design. Overloaded vehicles increase rutting failure. Poor traffic prediction leads to premature pavement distress. Toll roads generally require higher design traffic. Now these practical field mistakes become the cause of future failures. Art interview question box. Q. Why is traffic analysis important in IRC 37? Answer: because pavement thickness depends mainly on cumulative axle loading. Q. Which vehicles mainly govern pavement design? Answer: commercial vehicles. अब नीचे क्विक रिवीजन देखिए. ट्रैफिक वॉल्यूम, एक्सल लोड, ग्रोथ रेट और फाइनली MSA. यही पूरा फ्लो पेवमेंट डिजाइन ट्रैफिक डिसाइड करता है. In the next slide, we are going to understand the actual design traffic calculation and MSA calculation numerically. That's where real pavement design engineering begins. SLID 5. Design Traffic Calculation. So friends, till now we have understood what is traffic analysis, what is traffic volume, how does axle load affect the pavement, and what is the concept of MSAI million standard axles. But now comes the biggest question. Calculate actual pavement design traffic. On what basis is pavement thickness decided? And how does MSA come out in IRC 37? The actual design calculation part begins. 1. What is design traffic? Now first of all let us look at the first topic of the slide. It is written here. Design traffic is the total cumulative number of standard axle repetitions expected during the pavement design life. Us understand this line in simple language. Design traffic means how many times will the standard axle load be applied to the pavement during its entire pavement life. Now what is the important thing here? IRC 37 design expresses traffic. MILLION standard axles IEMSA. Now this is the most important parameter of pavement thickness design. See the engineering note below. Higher design traffic requires thicker pavement structure. It is absolutely practical. If there is a lot of traffic, so there will be more stress on the pavement. And there will be more stress. So the pavement thickness will also have to be kept higher. Now let us look at the second topic. To key cap purpose of design traffic calculation. Now the question comes. Calculate design traffic. Determine pavement thickness. That is, how thick will the pavement be. Estimate structural requirement. Which layer should be how strong. Prevent premature pavement failure. So quickly, cracking, rutting, settlement. It should not become tart. Improve pavement service life. The roads remain safe for many years. Ensure economical design. This means there should not be unnecessary extra thickness and weak pavement should not be constructed. Now the most important section of the slide begins. 3 key cap parameters required for design traffic. Now here all the parameters used in IRC 37 formula are given. A. Initial traffic A. Now what is initial traffic? How many commercial vehicles are running daily at opening time? Measured in CVPD. Commercial vehicles per day. Now understand the practical. Heavy truck movement on the highway from the beginning. So future MSA will also come out more. B. Traffic growth rate R. The traffic increases every year. This annual increase is called traffic growth rate. Here are the typical values. 5% to 7.5%. Now if the growth rate is higher, so future traffic will increase rapidly and pavement thickness will also have to be increased. C. Design life N. Now for how many years will this pavement perform satisfactorily? Typical IRC values. Flexible pavement 15 to 20 years. Now understand the practical field reality. If the design life is taken as 20 years, so the pavement will have to carry traffic safely for the entire 20 years. The vehicle damage factor, F. Now this is a very important parameter. This converts commercial vehicles into equivalent standard axle repetitions. Now see the important points below. Heavier vehicles produce larger VDF. Now what does this mean? The more overloaded the truck is, the more the pavement will be damaged. E. Lane distribution factor, D. Now in a multi-lane highway, traffic is not equal in every lane. Heavy vehicles mostly move in the slow lane. Therefore, there is more stress on the design lane. Typical values. Single lane 1.0, 2 lane 0.75, 4 lane 0.40, and this is called lane distribution factor. Now let us see the most important part of the slide. 4 main IRC 37 formula. Now the actual design traffic formula is given here. N 365 times A times frac 1 plus R N minus 1 R times F times D. Now here, N design traffic, A initial commercial traffic, R growth rate, N design life, F vehicle damage factor, D lane distribution factor. And this formula is the foundation of the entire pavement thickness design. Now let's look at the next topic. 5 keycap step-by-step calculation procedure. Now how is IRC SATI's calculation done? Is given here step by step. Step 8. Determine present commercial traffic. Step 2. Calculate projected traffic using growth rate. Step 3. Apply vehicle damage factor यानी VDF. Step 4. Apply lane distribution factor यानी LDF. Step 5. Convert final value into MSA. अब यही पूरा पेवमेंट डिजाइन ट्रैफिक कैलकुलेशन प्रोसेस है. अब राइट साइड ओवरलोडेड ट्रक डायग्राम देखिए. Now the actual field condition is shown here. Overloaded trucks increase pavement damage very rapidly. Now look at the typical axle configuration. Single axle 80 kN. Tandem axle 160 kN. Tridem axle 240 kN. Now as axle configuration increases, load distribution also changes. See the load transfer to pavement diagram below. Highest stress at the top, and as we go down the stress decreases. This is flexible pavement behavior. Now look at the pavement response diagram. Higher MSA means more stress, thicker pavement required. Now look at the traffic growth graph. Traffic is continuously increasing in the future. That means the future prediction was wrong. So the entire pavement may become unsafe. Now let us look at the sixth topic of the slide. A numerical example. Now here is the actual example. Given A 1500 CVPD, R 7.5%, N 15 years, F 4.5, D 0.75. Now after applying the formula, N 86.910 standard axles, and the result came HIGH MSA category. That is more than 50 MSAs. Now what does this mean? This highway will require a thick pavement structure. Now let us look at the seventh topic of the slide. 7 important technical concepts. Traffic growth increases pavement thickness. VDF significantly affects final MSA value. Incorrect traffic data leads to unsafe pavement design. Lane carrying maximum traffic governs pavement design. अब यही रियल इंजीनियरिंग लॉजिक है. 8 keycap common mistakes in design traffic calculation. Wrong traffic survey. Incorrect VDF selection. Ignoring traffic growth. Wrong lane distribution factor. Short duration traffic count. और यही मिस्टेक्स फ्यूचर पेवमेंट फेलियर का कारण बनती हैं. No practical site observation. Toll highways generally have higher MSA. Mining routes require stronger pavement. Industrial corridors show rapid traffic growth. Overloaded trucks reduce pavement life rapidly. अब यही actual field observations हैं. Interview question box. Q. What is MSA? Answer. Million standard axles used for pavement design traffic. Q. Which parameter most influences pavement thickness? Answer. Design traffic. अब नीचे one shot revision देखिए. A मतलब initial traffic. R मतलब growth rate. N मतलब design life. F मतलब vehicle damage factor. And D means lane distribution factor. And all these parameters are finally calculated. DSIGN traffic in MSA. Friends, till now we have understood design traffic calculation in complete detail. Now it must be clear to you on what basis pavement thickness is decided and how important role MSA calculation plays in IRC 37. If you find this detailed highway engineering series by CI useful, please like the video, subscribe to the channel, and share it with your civil engineering friends. Because in the next slide, we are going to understand lane distribution factor (LDF), where we will understand the actual multi-lane highway traffic behavior, design lane selection, and slow lane failure mechanism in detail. And this concept plays a huge role in practical pavement design. SLID 6. Lane distribution factor (LDF). So friends, till now we have understood design traffic calculation. MSA calculated. What is traffic growth rate? How does vehicle damage factor work? Comes a very practical question. Does the traffic move equally in every lane of the highway? Does every lane cause equal damage to the pavement? And how is design lane selected in IRC 37? So now let us understand this important concept. Lane distribution factor (LDF). 1 keycap introduction to lane distribution factor. Now first of all let us understand the definition. Lane distribution factor represents what percentage of total commercial traffic is the design lane carrying? Now traffic is not equally distributed in multi-lane highways. This is a very important practical point. Heavy commercial vehicles mostly ply in the slow lane. And this is why the slow lane receives the most pavement damage. See the engineering note below. Pavement design is governed by the lane carrying maximum traffic. That is, the lane which will have maximum commercial traffic. That will control the pavement design. Now let us look at the second topic. To keycap why lane distribution is important? Now the question comes. LDF so important? Determines actual load on design lane. That is, on which lane is the actual heavy loading taking place. Helps in realistic pavement thickness design. Is designed according to real traffic conditions. Prevents under-design of pavement. If you assume the wrong lane, so the pavement may fail quickly. Improves pavement service life. Increases pavement life. Reduces premature distress. Means rutting, cracking, settlement. There are less. Now let us look at the third topic. Teen traffic distribution behavior. Now different road conditions are shown here. Single lane road. All the traffic moves in a single lane. Therefore the entire load falls on that pavement. Two-lane road. Traffic is divided in both directions. But commercial vehicle concentration can still be uneven. Four-lane highway. Now the important thing starts here. Majority heavy vehicles move in the slow lane. Six-lane expressway. Commercial traffic gets concentrated in the outer lane. Now see the important points below. Design lane carries the highest cumulative axle load. And this is the IRC, SATI's design philosophy. Now look at the right side highway image. Clearly visible here. Heavy trucks are running in the slow lane. Fast lane carries comparatively lighter traffic. And that's why. SLOW lane design lane. Look at the axle load transfer diagram below. Heavy axle loads are being transferred to the pavement layers. And maximum damage is developing in the slow lane. Now look at the pavement response diagram. Here rutting is shown more in the slow lane. Why? Because the commercial traffic concentration is highest there. Now let us look at the fourth topic of the slide. Char standard IRC, SATI's lane distribution factors. Now here are the IRC recommended LDF values. Single lane. D1.00. Because all the traffic is in one lane. Two-lane single carriageway. D0.75. Four-lane divided carriageway. D0.40. Six-lane divided carriageway. D0.30. Eight-lane divided carriageway. D0.25. Now understand the practical logic. As the lanes increase, traffic starts getting distributed into multiple lanes. Hence the design lane factor gets reduced. Now let us look at the fifth topic of the slide. Part important formula box. Now the same IRC, SATI's design traffic formula is shown here. And in the lane distribution factor plays the most important role. N 365 times A times frac 1 plus R N minus 1 R times F times D. Now if wrong D value is selected, so the entire pavement thickness design may be wrong. Now let us look at the sixth topic of the slide. Engineering concept. Now why do commercial vehicles prefer slow lane? Lower speed. Heavy vehicles generally move at slow speed. Heavy loading. Loaded trucks reduce overtaking. Climbing conditions. In gradient sections, heavy vehicles remain in the slow lane. Traffic regulations. On many highways, trucks are restricted to the outer lane. And this is why PAVEMENT damage maximum develops in the slow lane. Now look at the traffic concentration graph below. Fast lane 10% to 15%. Medium lane 20% to 25%. Slow lane 50% to 60%. Now this is the most important practical observation. See the lane-wise traffic distribution table below. The 4-lane divided highway example. Fast lane 10% to 15%. Medium lane 20% to 25%. Slow lane I design lane 50% to 60%. Overtaking lane 10% to 15%. That means maximum commercial traffic is always carried in the slow lane. Now let us look at the seventh topic of the slide. 7 Practical Site Observation Box. Rutting is commonly observed in slow lane. Outer lane generally requires stronger maintenance. Incorrect LEF selection causes pavement failure. Industrial highways show higher slow lane distress. अब यही एक्चुअल फील्ड कंडीशन है. अब 8वां टॉपिक देखते हैं. 8 कॉमन मिस्टेक्स इन डिजाइन. SSUMING equal lane traffic. Ignoring heavy vehicle concentration. Using incorrect IRC values. Ignoring directional distribution. Now look at the diagram below. In wrong assumption, traffic equal is assumed. But in actual field condition, slow lane carries maximum heavy traffic. और यही करेक्ट अप्रोच है. अब स्लाइड का 9वां टॉपिक देखते हैं. 9 इंटरव्यू क्वेश्चन बॉक्स. Q1. Which lane is selected as design lane? Answer: lane carrying maximum commercial traffic. Q2. Why is LEF important in pavement design? Answer: because traffic loading is not equally distributed in all lanes. Now let's look at one short revision below. LDF means traffic share in design lane. Higher heavy vehicle concentration means higher pavement damage. Higher pavement damage meaning higher pavement thickness requirement. And this is why SLOW lane critical design lane. And what is the most important final takeaway? Correct LEF selection, safe, economical and durable pavement. And now in the next slide, we will understand the most critical concept of pavement foundation. SUBGRADE and CBR concept, where the entire pavement strength actually depends on the soil condition. SLID 7. Subgrade and CBR concept. So friends, till now we have understood traffic analysis, design traffic, and lane distribution factor in detail. But now we have reached the most critical foundation concept of pavement design. And this concept decides that the road will become strong or it will fail soon. Because the actual strength of the pavement does not start from the upper layer but from the soil condition below. And that is why today we will understand SUBGRADE and CBR concept. What is subgrade? Now let us first understand subgrade. After all, see the definition. Subgrade is the compacted natural soil layer that forms the foundation of the entire pavement structure. That means the entire wheel load is ultimately transferred to the subgrade. And that's why subgrade strength directly affects pavement thickness. See the engineering note below. Weak subgrade requires thicker pavement. Now what does this mean? If the soil below is weak, so the pavement thickness will have to be more. Now let us look at the second topic. Though functions of subgrade. Now what is the work of subgrade? Provides foundation support. The entire pavement stands on this foundation. Distributes traffic load to soil. The wheel load from above is safely transferred to the soil below. Maintains pavement stability. Road deformation control takes place. Controls settlement and deformation. Uneven settlement is less. Supports pavement during construction. Subgrade also plays a very important role in the construction stage. Now let us look at the third topic. 10 characteristics of good subgrade. Now what properties should a good subgrade have? High bearing capacity, proper compaction, low compressibility, good drainage property, uniform soil condition. Now see the important points below. Proper moisture control improves subgrade performance. And this is a very important field concept. If the moisture control is impaired, so the CBR value will start decreasing. Now the most important concept of the slide begins. What is CBR? CBR means California bearing ratio. Now understand the definition. CBR is a ratio that compares the resistance of soil with that of standard crushed stone. Simple language. CBR indicates soil strength, measured in percent. Now understand the practical thing. Higher CBR means stronger soil. Lower CBR means weaker soil. Now let us look at the fifth topic. 5 Importance of CBR in IRC 37. Now why is CBR so important in IRC 37? Government's pavement thickness determines structural capacity. Used in pavement design charts. INDICAT's soil strength condition. See the engineering note below. Lower CBR means thicker pavement. And this is the entire pavement design logic. Now look at the right side diagram. Wheel load is being transferred from top to bottom. And finally all the stress is reaching the subgrade. Now see the comparison below. Good subgrade. High CBR. High support. Less deformation. Lower pavement thickness. Poor subgrade. Low CBR. Lower support. More deformation. Higher pavement thickness. Now look at the moisture effect diagram. Dry condition. High strength. High CBR. Wet condition. Low strength. Low CBR. And this is why water infiltration is very dangerous for pavement. Now let us look at the sixth topic. 6 CBR classification of soil. अब यहाँ soil categories दी गई हैं. Very poor soil. CBR less than 2%. Very weak subgrade. Very thick pavement required. Poor soil. CBR 2% to 5%. Weak soil. Thick pavement required. Fair soil. CBR 5% to 10%. Medium strength soil. Good soil. CBR more than 10%. Strong soil. Thin pavement is sufficient. Now in practical field condition. Black cotton soil generally shows low CBR. Now let us look at the seventh topic. 7 CBR test procedure. Now how is CBR test done? Step 1. Prepare compacted soil sample. Step 2. Place surcharge weight. Step 3. Apply penetration load using plunger. Step 4. Measure penetration resistance. Step 5. Calculate CBR percentage. The setup that is visible in the middle. That is the actual CBR testing apparatus. Now let us look at the 8th topic of the slide. 8 Important formula box. Now here is the actual CBR formula. CBR frac text test load text standard load times 100. Now here, test load means field soil load. And standard load means standard crushed stone load. Now the higher the ratio will be that strong. Now let us look at the ninth topic. No engineering concepts. High CBR soil reduces pavement thickness. Saturated soil decreases CBR value. Expansive soil causes pavement distress. Uniform compaction improves pavement performance. Now this is actual pavement foundation engineering. Now remember the below. COMPACTION is key. Proper compaction, higher density, higher CBR, better pavement performance. Now let us look at the 10th topic. PRACTICAL site observation box. Black cotton soil shows low CBR. Poor drainage weakens subgrade rapidly. Moisture variation causes settlement. Improper compaction leads to rutting and cracking. अब यही साइट लेवल प्रैक्टिकल प्रॉब्लम्स हैं. अब 11वां टॉपिक देखते हैं. 1 कॉमन सबग्रेड फेलियर्स. डिफरेंशियल सेटलमेंट, shear failure, excessive deformation, pumping action, moisture damage, and their actual failure photos are also shown below. Now let us look at the 12th topic. 1 to interview question box. Q. Why is CBR important in pavement design? Answer. Because pavement thickness depends on subgrade strength. Q. Which soil generally shows low CBR? Answer. Clayey and expansive soils. Now let's look at one short revision below. Strong subgrade, higher CBR, lower pavement thickness. Weak subgrade, lower CBR, higher pavement thickness. And this is the entire pavement foundation concept. Now look at the final key line at the bottom. STRONG subgrade, strong pavement, economical design, longer service life. And now in the next slide, we will understand EFFECTIV CBR and subgrade evaluation, where actual field condition, soaked CBR, worst moisture condition, and representative design CBR will be understood in detail. SLID 8. Effective CBR and subgrade evaluation. So friends, in the previous slide we understood the CBR concept in detail. But now here comes the most important practical question. Entire highway be designed with a single CBR value. Does the soil condition remain the same throughout the road length? A weak soil patch appears somewhere, then what will happen to the pavement? To solve this practical engineering problem comes EFFECTIV CBR concept. What is effective CBR? Now let us understand the definition. Effective CBR is the representative CBR value used for pavement design. It considers field variability and weakest soil conditions. Now what is the most important thing here? IRC 37 does not use isolated laboratory value. Rather, uses effective CBR. See the engineering note below. Pavement design should consider worst field condition. And this is the actual highway engineering philosophy. Because the road will not always be in the best condition. Rainfall, waterlogging, moisture variation, weak soil pockets. Everything comes in the actual field. Now let us look at the second topic. No need for effective CBR. Now why is there a need for effective CBR? Soil properties vary along road length. The soil is not the same in its entire alignment. Moisture changes affect strength. Soil strength reduces when water comes. Weak patches reduce pavement life. If there is a weak zone somewhere, then the failure will start there. Uniform pavement performance required. Consistent performance is required throughout the road stretch. Prevents premature failure. Early rutting, settlement, cracking. There is control. Now let us look at the third topic. 10 factors affecting effective CBR. Now on what factors does effective CBR depend? A. Moisture content. Soil strength decreases when moisture increases. Saturated condition produces minimum CBR. Now see the important points below. Design CBR is generally considered at soaked condition. And this is a very important IRC practice. B. Soil type. Clayey soil generally shows low CBR. Granular soil gives higher CBR. C. Compaction level. Higher compaction improves CBR value. Reduces pavement stability. D. Drainage condition. Poor drainage rapidly weakens the subgrade. Reduces the bearing capacity. Now look at the right side diagram. Wheel load is being transferred downwards, and weak soil zone is shown below. Now look at the moisture effect diagram. Dry condition. High strength. High CBR. Moist condition. Medium strength, medium CBR. Saturated condition. Low strength. Low CBR. And this is why drainage plays a big role in pavement life. Now let us look at the fourth topic. Char selection of effective CBR. Now how is effective CBR selected? Multiple field samples are collected. Laboratory CBR tests are conducted. Lowest representative value is selected for design. Now see the engineering concept below. Effective CBR represents actual field performance. And this is the most important line. Now let us look at the fifth topic. 5 typical effective CBR values. Now here are the typical effective CBR values for different soil types. Black cotton soil 2% to 5%. Clayey soil 3% to 7%. Sandy soil 8% to 15%. Granular soil more than 15%. Now in the practical field, granular soil provides the strongest foundation. Now let us look at the sixth topic. 6 pavement thickness relation. Now the most important design relation is shown here. Higher effective CBR, lower pavement thickness. Lower effective CBR, higher pavement thickness. Now what does this mean? If the soil is weak, so the pavement layers will have to be made thick. Now let us look at the seventh topic. 7 important formula box. Now the conceptual relation is given here. TK left, frac 1 CBRN right. Now here, T total pavement thickness. That means CBR will decrease, then thickness will increase. And this is the entire pavement design logic. Now let us look at the eighth topic. 8 engineering concepts. Weak subgrade requires stronger pavement structure. Effective drainage improves long-term CBR. Stabilization improves subgrade performance. Uniform soil condition increases pavement life. अब यही लॉन्ग टर्म पेवमेंट परफॉर्मेंस कॉन्सेप्ट्स हैं। अब 9वां टॉपिक देखते हैं। 9 subgrade improvement methods. Now how do we improve the weak subgrade? Soil stabilization, lime treatment, cement stabilization, proper drainage, mechanical compaction, replacement of weak soil. Now the stabilization process is also shown below. weak salt stabilizer addition, mixing, compaction, and finally improved subgrade. Now let us look at the 10th topic. PRACTICAL site observation. Black cotton soil areas require stabilization. Waterlogged stretches show rapid settlement. Inadequate compaction causes edge failure. Expansive soil creates pavement cracks during seasonal changes. अब यही एक्चुअल फील्ड प्रॉब्लम्स हैं. अब 11वां टॉपिक देखते हैं. 1 common problems due to low effective CBR. Rutting, settlement, longitudinal cracking, edge failure, excessive pavement thickness requirement. और यही फेलियर्स वीक सबग्रेड का डायरेक्ट रिजल्ट हैं. अब 12वां टॉपिक देखते हैं. 1 to interview question box. Q. Why is soaked CBR used in design? Answer. Because pavement experiences worst moisture condition during service life. Q. What happens if effective CBR decreases? Answer. Required pavement thickness increases. अब नीचे वन शॉट रिवीजन देखते हैं. Effective CBR representative design CBR. High CBR strong foundation. Low CBR weak foundation. Weak soil thick pavement. अब नीचे ड्रेनेज डायग्राम देखिए. Drainage improves CBR. Better drainage, better design, longer pavement life, economical construction. Now look at the remember point at the bottom. Design for the worst condition, not for the entire service life. And this is the actual IRC design philosophy. And now in the next slide, we will understand FLEXIBLE pavement composition, where we will understand the complete pavement layer arrangement, surface course, binder course, base, subbase, and load transfer mechanism in detail. SLID No. Flexible pavement composition. So friends, till now we have understood IRC, SANTIS, traffic, CBR, and subgrade strength. But now comes the most important question. After all, how is pavement structure formed? What are the layers inside the road? The load transferred from top to bottom. And which layer gives the actual strength? So we will understand this complete structural system in detail in this slide. FLEXIBLE pavement composition. एक introduction to pavement composition. Flexible pavement is a multi-layer structural system whose main purpose is transfer the wheel load safely to the subgrade. Now what is the most important thing here? Each layer has a different engineering function. The quality of any one layer is bad, so the entire pavement performance may be affected. See the engineering note below. Strength of pavement depends on combined performance of all layers. And this is the actual pavement engineering concept. Now let us look at the second topic. Though typical flexible pavement composition. The complete layer sequence from top to bottom is given here. A. Bituminous surface course is the topmost riding layer. B. Binder course. It provides a structural connection between the surface and base layer. C. Base course. This is the main structural layer. D. Sub-base course. It provides drainage and support. E. Compacted subgrade. This is the foundation soil of the entire pavement structure. Now look at the right side diagram. Wheel load is acting on the surface above, and the load is slowly spreading downwards. This is the main behavior of flexible pavement. Now let us look at the third topic. Teen surface course. Let us understand the topmost layer. Surface course is directly exposed to traffic and environment. Its main functions: providing smooth riding quality, provides skid resistance, preventing water entry, direct wheel load carrying. Now look at the common materials. BC means bituminous concrete. SMA means stone matrix asphalt. And wearing coarse mixes. Now see the important points below. Surface layer requires highest quality control, because this layer directly faces the traffic. Now let us look at the fourth topic. Char binder course is the intermediate bituminous layer. It remains under the wearing course. Its functions: wheel load distribution, pavement strength increase करना, structural capacity improve करना. अब common materials देखिए. DBM यानी dense bituminous macadam, CTB or CTSB. Now let us look at the fifth topic. Punch base course. Now this is the most important structural layer. The base course carries the major load of the pavement. Its functions: major load distribution, structural support, stress reduction on subgrade. Now look at the engineering note here. Base course governs pavement strength, and this is considered the most critical layer in practical design. Now let us look at the sixth topic. Sub-base course. Sub-base layer is provided between the base and subgrade. Its functions: drainage improvement, frost protection, working platform during construction, prevention of fines intrusion. Now look at the common material. GSB means granular sub-base. Look at the drainage arrows below. Flows out through the sub-base and side drain. And this improves pavement durability. Now let us look at the seventh topic. Sath subgrade. Now comes the bottom. Subgrade. This is compacted natural soil, which supports the entire pavement system. Its functions: final load support, foundation of pavement. Now what is the design parameter here? CBR value. The keynote below also says the same thing. Poor subgrade causes pavement failure. Now look at the full cross-section diagram on the right side. Surface course 25 to 50 mm. Binder course 50 to 100 mm. Base course 150 to 300 mm. Sub-base course 150 to 300 mm. Compacted subgrade, CBR-based natural soil. Now let us see the load transfer mechanism below. Step 1. Wheel load acts on the surface. Step 2. The load moves down, it spreads to a wider area. Step 3. As the depth increases, the stress reduces. Step 4. Subgrade receives reduced pressure. And this is the whole flexible pavement load distribution concept. Now let us look at the eighth topic. Art load transfer mechanism. Look at the left side diagram below. Red arrows show that stress is decreasing with depth. I.E. Higher thickness, lower subgrade stress. Now let us look at the ninth topic. Now important engineering concept. Higher layer stiffness improves load distribution efficiency. What does it mean? If the upper layers are strong, so the stress will spread properly, and the subgrade will remain safe. Now let us look at the 10th topic. LAYR-wise material importance. Surface layer. High durability and skid resistance. Binder layer. Structural continuity. Base layer. Main structural strength. Sub-base. Drainage and separation. Subgrade. Foundation stability. अब 11वां टॉपिक देखते हैं. 1 common pavement distress due to poor composition. Rutting. Fatigue cracking. Edge failure. Raveling. Settlement. And these failures occur due to poor layer composition. Now let us look at the 12th topic. 1-2 practical site observation. Poor drainage weakens sub-base rapidly. Low compaction in WMM causes deformation. Thin bituminous layer increases cracking. Weak subgrade causes differential settlement. Now these practical site problems are seen frequently in the field. Now let us look at the 13th topic. 1-3 interview question box. Q. Which layer mainly provides structural strength? Answer. Base course. Q. Which layer directly contacts vehicle tire? Answer. Surface course. The material texture guide is also given below. BC. DBM. WMM, GSB and subgrade material. And compaction equipment is also shown. Vibratory roller, sheep foot roller, tandem roller, plate compactor. अब नीचे वन शॉट रिवीजन देखते हैं. Surface layer, riding quality, binder layer, load distribution. Base layer. Structural strength. Sub-base. Drainage support. Subgrade. Foundation soil. Now look at the key takeaway at the bottom. Proper layer composition ensures long pavement life. Each layer has specific engineering function. And quality plus thickness plus proper compaction better pavement performance. Find this detailed engineering explanation useful. Like the video, subscribe to the channel, and press the bell icon. Because in the upcoming slides, we are going to understand more deep pavement engineering concepts. And now in the next slide, we will understand failure criteria in flexible pavement, where fatigue cracking, rutting, design life, and pavement failure mechanism will be understood in detail. SLID 10. Granular layers in flexible pavement. So friends, till now we have understood flexible pavement composition. In this slide we will understand the most important structural support system of pavement. And that is granular layers. I.E. GSB and WMM. Because the actual field performance of the pavement depends to a large extent on the quality of the granular layers. If GSB and WMM turn out right, so the pavement becomes strong and durable. But if there is compaction, gradation, or poor drainage, so the entire pavement can fail quickly. Understand this entire slide in detail. एक introduction to granular layers. Granular layers are pavement layers made of crushed aggregates. Their main work: providing structural support, providing drainage, wheel load distribution. And these layers are provided below the bituminous layer. Now look at the engineering note here. Granular layers form the backbone of flexible pavement. And practically this is absolutely correct. Because the major part of pavement strength comes from the granular layers. Now let us look at the second topic. 2 types of granular layers. Main granular layers are shown here. A. GSB. Granular sub-base. B. WMM. Wet mix macadam. Now the function of both layers is different. GSB is mainly for drainage and separation, whereas WMM provides structural strength. Now let us look at the third topic. Teen granular sub-base IEGSB is the lowest granular layer, which is provided above the subgrade. Let us understand its functions. Improves drainage, prevents capillary rise, provides working platform, separates subgrade from upper layers, reduces pumping of fines. अब मटेरियल रिक्वायरमेंट देखिए. वेल ग्रेडेड क्रश्ड एग्रीगेट्स यूज किए जाते हैं और कंस्ट्रक्शन थिकनेस जनरली 150 mm to 200 mm. See the engineering note below. Drainage performance mainly depends on GSB. And this is the most important concept in the field. If the drainage is bad, so moisture will enter the pavement, and the pavement will deteriorate quickly. Now let us look at the fourth topic. Char wet mix macadam i.e. WMM. Now let's understand WMM. This is a dense graded aggregate layer, which is compacted by mixing it with water. Now what are its functions? Main granular structural layer. Distributes wheel load. Improves pavement stability. Provides strong base support. अब कंस्ट्रक्शन थिकनेस देखिए. Usually 250 mm to 300 mm. In layers. अब नीचे important point देखिए. WMM requires proper moisture and compaction. That means moisture control and rolling are very critical here. Now let us look at the right side diagram. This typical granular layers section is shown. The wheel load is acting above, and as the load goes down, it is spreading to a wider area. This load transfer mechanism makes the pavement safe. Look at the water flow arrows below. Is performing drainage function. Now let us see the construction process image. Shown here are dumpers, motor grader, water tanker, and vibratory roller. This is the actual site equipment used in granular layer construction. Now let us look at the fifth. Punch difference between GSB and WMM. अब दोनों लेयर्स का कंपैरिजन समझते हैं. GSB ड्रेनेज ओरिएंटेड लेयर. लोअर स्ट्रेंथ रिक्वायरमेंट. प्लेस्ड अबव सबग्रेड. WMM structural load carrying layer. Higher strength requirement. Placed below bituminous layer. And these two layers together form the pavement foundation. Now let us look at the sixth topic. Construction procedure of GSB. See step-by-step process. Step 1. Surface preparation. Step 2. Material spreading. Step 3. Water sprinkling. Step 4. Grading using a motor grader. Step 5. Compaction by vibratory roller. Step 6. Field density testing. And this is the complete GSB construction sequence. Now let us look at the seventh topic. Saat construction procedure of WMM. Step 1. Aggregate mixing in WMM plant. Step 2. Transportation by dumpers. Step 3. Mechanical laying using paver. Step 4. Moisture control. Step 5. Rolling and compaction. Step 6. Level and density checking. And this standard sequence is followed in practical highway projects. Now let us look at the eighth topic. Art quality control requirements. Quality control is very important in granular layers. Which tests are required? Graduation test, moisture content test, field density test, thickness measurement, level checking, compaction control. If these tests fail, so pavement performance is directly affected. Now let us look at the ninth topic. Now important engineering concepts. Proper gradation improves density. Poor compaction causes rutting. Excess moisture weakens WMM. Drainage failure damages pavement rapidly. And these four concepts are most important in the field of quality control. Now let us look at the 10th topic. COMMON failures in granular layers. Rutting, settlement, segregation, weak edges, moisture damage. Now these failures are most visible in the practical field. Now let us look at the 11th topic. 1 practical site observation. Uneven moisture causes poor compaction. Segregated aggregates reduce strength. Improper rolling creates loose patches. Poor drainage leads to pumping action. And the site engineer should always pay attention to these observations. Now let us look at the 12th topic. 1-2 interview question box. Q. Which layer mainly provides drainage? Answer. GSB layer. Q. Which granular layer mainly provides structural strength? Answer. WMN layer. Look at the cross-section diagram below. Bituminous layers are above. Below that is base course. Then WMN. Then GSB. Compacted subgrade at the bottom. Now look at the load distribution diagram. Load is spreading with depth. And the stress is reducing as it goes down. Now let us see an aggregate gradation example. Well-graded aggregates gives higher density plus higher strength. But poorly graded aggregates create voids and weakness. Now look at the drainage function diagram. GSB allows water to pass down and prevents moisture from accumulating in the pavement. Now look at the compaction equipment below. Vibratory roller, sheep foot roller, tandem roller, and water tanker. Look at the final key concept at the bottom. GSB, drainage plus separation. WMN, structural strength. And good compaction, better pavement life. But poor drainage, pavement failure. Find this detailed practical explanation useful. Do like the video, subscribe to the channel, and also share this video with your civil engineering friends. In the upcoming slides, we are going to understand pavement failures, rutting, fatigue cracking, and complete design mechanism in detail. And now in the next slide, we will understand bituminous layers and surface courses, where BC, DBM, wearing course, and pavement riding quality will be understood in detail. Okay friends, till now you have completed part 1. Let's do a quick recap. You understand pavement basics. The layer system became clear. I understood how load distribution happens. And the importance of subgrade and material also became clear. Is your base? Is your foundation? And remember, strong basics mean strong design. Now the next step is clear. Now we will move towards part 2. Because this is where the actual design starts. Part 2 we will talk about traffic loading, CBR, drainage and design inputs. That means now the calculation will start. Now the real engineering will begin. And one important thing, if the input data is wrong then the entire pavement design will go wrong. That is why part 2 is the most important part. So now let's go straight to the next video. Part 2 and move on to design. If to you its series useful sound doing is. So civil engineering infrastructure subscribe take it. Video like came yes so like definitely do it. On doubt or feedback in comment write. And this way only content for this our friends and colleagues with share also do it. On YouTube us follow @civilenginfra. On Instagram to connect @civilenginfra. Facebook and on LinkedIn to by searching Civil Engineering Infrastructure Connect. Here you will get highway engineering, pavement design, IRC concepts and site practical knowledge. Let's move on to part 2.